On the 1st of April 2026, Artemis 2 launched into space.
Booster ignition and liftoff.
The first crewed mission in over 50 years heading back to the moon. It's a place that has been special to me ever since I was young. I've always declared myself as a self-certified lunatic. I mean, what's not to love? It's always beautiful in the night sky, and sometimes it feels so close you could almost touch it. So imagine my excitement when they announced that we're sending people back there. The journey of Artemis 2 around the moon is a historic moment in the current race to get back to the surface, and maybe one day beyond to other worlds. So tonight, we're diving in to what it actually takes to get back to the moon. What are the challenges we're facing in the new lunar race? And what we're already learning as we make that journey. Welcome to the Sky at Night.
I'm going to tell you the story of our moon, but to do that, we're going to go back some 4.5 billion years. But don't worry, highlights only. Now, at the time, our solar system was filled with swirling gas and dust, and there was constant collisions going on. In all of that mess, the planets were forming. Now, it's believed that in this chaos, a Mars-sized object called Theia struck the young, nascent Earth in what scientists call the giant impact. From the debris of this collision, two worlds were formed, Earth and the Moon. So these siblings traveled through the galaxy together as constant companions, with gravity shaping their partnership and keeping them together. Now, fast forward again a few billion years, and humans evolved. After thousands of years of looking up at the moon with wonder, technological advances meant that we could finally start to dream about reaching out and touching the moon. And so, in the 1950s, the first space race began. Now, the Soviets were the first to get a person into orbit, but it was the NASA Apollo missions that led the way in the race to the lunar surface. But it wasn't the one giant leap that we all remember. Apollo 1 was a sad and terrible disaster, but they learned from it. They redesigned the spacecraft. They did so much testing, and so we continued to inch closer and closer until Apollo 8. So this was the first time that they successfully got humans in orbit around the moon.
Apollo 8, Houston, we just got it. He's on candid camera.
This was followed soon after by Apollo 11 and 5 subsequent missions that successfully landed crews on the moon's surface.
Roger, the EVA is progressing beautifully. They're setting up the flag now.
And then, in 1972, it all just stopped.
But today, over 50 years on, there's a new race to the moon. And while China's Chang'e mission has been leading the way with landers and sample returns, it's NASA's Artemis mission that has just taken a huge leap forward. Just as Apollo before it, the Artemis program hasn't been plain sailing. Artemis 1 was an uncrewed test flight using NASA's new SLS, its Space Launch System, the most powerful rocket they have ever built. This new system pushed through engineering delays and a global pandemic before finally looping around the moon in 2022. Then came Artemis 2, again delayed by years, then months, then weeks. It finally launched 4 crew members, including the first woman, the first black person, and the first non-American, on a 10-day journey of nearly 700,000 miles around the moon and back. The flight path for Artemis 2 travels 4,600 miles beyond the far side of the moon. Further, than any human has ever been before. And it's incredible to think where these astronauts have been.
While it's exciting for us watching on, I'm meeting one of the few people on Earth who knows what it's like to go into space.
In 1991, Helen Sharman blasted off on a Soyuz rocket for an 8-day mission, becoming Britain's first astronaut. If anyone can help me understand what it's like to go into space, it's her.
I'm at Imperial College London's Space Engineering Laboratory to meet Helen, who is now a UK outreach ambassador here.
Now, of course, you are an astronaut yourself. So what is it like actually going into space?
It is just a really thrilling moment when you realise that actually there is only one way off that rocket, and it's going to be for you. It's going to be up into space, right? And one of these Artemis astronauts, it will be his first time ever in space.
Oh, wow.
So it'll be his first ever real launch experience. And although we can train and do tests in a centrifuge where we're spun around a room, you don't hear the bumps and the bangs, you don't feel the jolts. But no, the most thrilling moment, actually, is when the fairing is jettisoned. So this, of course, is the protective layer that we put around a rocket and the spacecraft to stop us from being damaged by the atmosphere as we go through it. And as soon as that fairing is jettisoned, then light streams through the window. And if you are lucky, you get the view of the Earth. And yes, so in my launch, yes, I was my window was facing towards the Earth. So I could see the Earth's horizon. Of course, we were still launching, we were still getting further and further away, but there was that blue horizon, there was the black of space above. Yeah, so thrilling.
I mean, those views sound incredible. After the Apollo era, there was just a dip in interest in the moon. We haven't been for such a long time. Why now?
There's always been science about the moon to learn, science that we can do while we're on the moon, and that's not changed, although science has developed, of course. But I think what's happening now is that there is, first of all, the promise of what could be a lunar economy, and everybody wants to have a bit of that because it's actually forecast to be billions of dollars, actually, by 2040s. But also, of course, there are other countries involved. China has stated a desire to not just land astronauts on the moon, but to actually have operations there. And there is this really strategic part of the moon, and it's the South Pole. Now, if a country establishes a big enough operation there, they could get the best bits of the moon, as well as this part of the moon, which is not only, it's bathed in sunlight if you go to the rim of the crater most of the time, so you can power your equipment. We've got water ice there for the astronauts and for equipment for making rocket fuel, and possibly mining some of the rare earths there as well. So a whole load of stuff, of reasons actually to want to go to the moon, and to go to the moon quickly. Now we've got this political race all over again.
So are we then in another space race?
I think we are. It's a space race now to get to the South Pole of the moon.
Water and power are essential for any lasting lunar base. And although being first grabs headlines, countries are really chasing long-term footholds.
What are your hopes for the future of human space exploration?
I think what I really want to see is that international cooperation. So we're not just fighting each other to get the best bits of space and mining an asteroid and claiming it as ours. I want us to see us using that for the benefit of the Earth. You don't want to establish operations, let's say it is mining, and that's likely to be, have quite a few vibrations, in an area that's maybe the best place to do some astronomy, let's say radio astronomy, something like that, where you need a lovely, stable base for it. So, yes, I think we need that cooperation. Humans are just basically curious. We want to explore and find out more. And if we can sort out all of the operational stuff and the practicalities, the stars really are our limit.
While Artemis 2 tests out the space technology that hopes to land humans on the moon, our lunar future is also being driven steadily forward by remote and robotic missions. One man at the heart of this is space instrument engineer Simeon Barber. Can you tell me what you're working on at the moment?
At the moment, I'm working on a mission called Prospect. This is a European Space Agency project to develop a drill and a sample analysis package to go on a lunar lander in a couple of years' time. It will land near the South Pole of the moon, and we're looking to understand Can we find water ice there buried beneath the surface?
And so you're using a drill to go below the surface?
Yeah, so we want to get to about a metre below the surface because these are the depths that are probed by orbiters that have suggested that there might be concentrations of water at the poles, but they're just remote sensing measurements. It's very difficult to know how accurate those measurements are. So we're trying to get this survey of what is below the surface.
But of the many uncrewed missions to the moon over the last few years, there have been about as many failures as successes. So why are we finding it so hard when we had humans on the surface over 50 years ago?
Okay, we're go. We're go. Swing tight. We're go.
So remember that Neil Armstrong did amazing things.
He was steering it down.
He was steering that spacecraft, and when he didn't like the look of the landing site, he flew to a safer place and landed with just seconds of fuel left.
The Eagle has landed.
Humans are able to do that. At the moment now, we're doing robotic landings, and they're mainly based on vision-based navigation. So there are cameras looking at the terrain, comparing it to maps they have in their memory. The problem we've had recently is that, particularly near the South Pole, it's actually really difficult because the sun is always very low in the sky and you get very long shadows.
Oh, yes.
And it means that the maps that the cameras are using are very susceptible to changes in angles of illumination from the sun. So these vision-based systems are really getting confused by the environment.
So we have had a number of failures, but are there lessons learned from these failures?
Yeah, there's always lessons learned, and you learn by doing. I'm a great believer in that. So what's actually happening at the moment is that NASA has kind of catalyzed a new breed of commercial companies. So they've put out contracts and said, we would like to buy services which will deliver as a payload to the South Pole of the Moon or to the equator, and we're going to pay this amount of money. Who would like to bid? And they've created this kind of competitive environment. And the overall idea is that we try and come up with a new way of doing space exploration.
Rather than sort of having sort of one big mission where you've put everything into it, you're trying sort of smaller missions, but many of them, and then learning as we go along.
Yeah, that's exactly what's happening. So the idea is you try often, if you're going to fail, you fail early, you learn from that, and then you go again. So these missions are all robotic. You know, no one dies if the mission goes wrong.
I suppose one of the challenges with robotic missions is miniaturization. Launching things into space is incredibly expensive.
Yeah, so literally gravity has held us back. You know, that's why we're on Earth, because of gravity. And that's, as a space scientist, that's your enemy. And interestingly enough, there have been calculations recently saying that to get a kilogram of any kind of payload to the surface of the moon costs on the order of €1 million or pounds or dollars. You know, your currency of choice. The 1 million is the key thing.
Yes.
Yeah. So that means, you know, every few grams we can save here and there is really, really worthwhile. So to give one example, this device is a mass spectrometer. So it's like a weighing machine for atoms on the moon. Now, this kind of device would be, you know, huge in a laboratory. It would be the size of a microwave oven at least.
So this isn't a scale model. This is actually the mass spectrometer.
This is a real working instrument. So by miniaturizing it to this size, which is about 100 grams, it's more acceptable to a spacecraft to have it on board. And it also means it's quite sensitive. When you make things small, they can become quite sensitive. So the performance can improve as well.
So the technology evolves, but it's based on things that we've done before.
In traditional space, at least, we tend to be quite conservative. Yes. Of course, what's happening now with the moon, in that there are more missions going, and they tend to be faster and cheaper, it does mean you can take more risks.
Yes.
Because you get more opportunities. You know, it's a new way of building instruments and allows us to be a bit more adventurous and try things, push the boundaries a bit.
While organisations like NASA and ESA are looking at a new approach to space exploration, China's space program is also breaking new lunar ground.
Before 1959, we had no idea what was on the far side of the moon. It could have been literally anything, to the delight of science fiction writers and the occasional conspiracy theorist as well. But then the Soviets sent their Lunar 3 probe around the moon, sending back the first blurred pictures of the far side. And this is that first picture, showing the full disk of the far side. And even though the quality isn't great, you can see that it's different from the familiar near side that you see when you look up from here on Earth. The modern images make the comparison obvious. The near side has these dark round features which we call seas, but they're almost entirely missing on the far side, which instead has this fractured, scarred, cratered surface. So the two sides of the moon look very different. It was a surprising result then, and it's a fact that's puzzled astronomers ever since.
Decades of remote analysis have given us a deeper understanding of the moon, revealing a more complex world than once suspected. The crust is thicker on the far side, and a collection of heat-producing elements, known as creep, cluster on the near side. So why is the moon so uneven? With only Apollo samples available, all of them from the near side, the answer remained out of reach until now.
In 2024, China's Chang'e 6 collected and returned to Earth the first ever sample from the lunar far side. Scientists have been excitedly analysing it ever since, and one of them is just along the corridor.
Geochemist Yang Li is based at Peking University and affiliated with University College London. He's one of only a few people to have held the far side of the moon in his hands.
Can you talk us through when you first saw the sample and what it was like?
It's very exciting, of course. So when you hold these samples, you know these are from the far side of the moon. This is the first time human beings ever hold a sample in hand.
Yeah.
At the same time, this is a big responsibility because everyone wants to know what you are going to get from these samples.
Yeah. So with that responsibility, was it a big effort to try and get these results?
Yeah, I lead a young group. We pretty much worked around the clock. We never felt tired because you always get new things and you always want to know more.
It feels like you were on a lunar mission yourself. So tell us about this sample. What have you found out about this particular piece of the moon?
The first thing we do is we date that by uranium-lead dating, so which is based on the decay of uranium to lead. And then we get an age of 2.8 billion years old.
So this is relatively late in lunar history.
Yeah, it's something like it's middle age.
Great. So we know the age of the sample. Now, you were able to say something about the temperature at which it formed.
Yeah. Once we know the age, what we do is we use both geochemical analysis and petrological modeling. We realize the mantle from the far side is 100 Celsius degrees colder than its comparable mantle source from the near side.
Analysis of the sample produced an incredible discovery. Real insight into what was happening on the moon's far side some 2.8 billion years ago. And by comparing it with Apollo's near-side samples, we discover a difference of 100 degrees Celsius existed in the past, just below the surface. To understand why, we need to look further back. When the moon was still cooling and its crust slowly forming, a leftover mix rich in potassium, rare earth elements and phosphorus, known as creep, was still fluid beneath the surface. And because creep isn't spread evenly around the moon today, it may hold the key to its lopsided past.
So once you have this creep, at that time, if you have impact happen at that right time, when creep is still molten, you can push that creep from one side to the other side.
So it's literally something smashing into the moon and this material gets moved around.
Yes.
So what's interesting about this idea for me is I think I'd assumed that when you talk about the difference between the near side and the far side, that it must have something to do with the Earth.
Actually, there is a hypothesis considering the Earth's role in generating this two-faced moon.
Okay.
Yeah. So when the Earth and the moon was newly formed, the Earth is also hot at that time. So the side facing the Earth potentially can have more radiation heat from the Earth to the moon.
Ah, okay.
Yeah,
so it's the Earth that's heating the moon potentially.
Yeah. So there are different hypotheses trying to explain why the moon has two dramatically different phases. It's possible that both this creep and the Earth shine are working at the same time. We need more missions there and more samples.
Yeah. Well, I'm all in favor of more missions.
We haven't quite solved the moon's two-sided mystery yet, but the view from billions of years ago of both sides is getting us closer.
While many dream of a future era of lunar exploration with boots on the ground, it's happening already. With missions like this one, we're learning more about the complex, surprisingly dynamic history of our nearest neighbour, and ultimately, whether it's robots or humans collecting it, we just want more data.
Could the Artemis programme be on track to get us a step closer? 8 days before launch, I was lucky enough to speak with Kelsey Young, who leads the NASA mission's lunar science campaign. I asked her about her hopes for the mission.
Artemis 2 is, of course, first and foremost a test flight. We want to launch our crew members safely and get them home. And so I'm really excited about the lunar science component of this mission and what our trained crew members and the Orion vehicle cameras will be able to do for us.
So what sort of training have they had?
When astronauts are first selected as astronaut candidates, they actually, as a part of their initial 2-year astronaut candidate training flow, get 4 weeks of geology training, 2 weeks in the classroom and 2 weeks in the field. But beyond that, when they're assigned, we again had them back in the classroom, can't escape that classroom training. We've taken them out into the highlands of Iceland because it's a really lunar-like terrain. And then really critically, and especially lately, we've been working with them repeatedly in mission simulations. We actually have them able to practice using the cameras, practice giving the descriptions of the moon, and practice all of that in a flight-like environment.
So they're going to be travelling over 4,500 miles from the far side of the moon. What sort of details can they see from that distance?
It's a really unique vantage point. Apollo missions flew much, much closer to the lunar surface. Artemis 2, as you point out, will be much farther away. It will be about the size of a basketball held at arm's length to the crew. So if you pick up your nearest basketball, hold it out at arm's length, that will be about the size of what the moon will appear to the astronauts with the unaided eye. And actually, there's really interesting science that we can gain from that unique perspective. First of all, there are massive chunks of the lunar far side that human beings have never actually seen before. This is because of the unique trajectories that the Apollo astronauts did fly. And that's really interesting scientifically for a few reasons. One of them, my scientific background is impact cratering. And impact craters can actually toss material hundreds, if not thousands of kilometers across the lunar surface. So an impact feature that forms in the northern hemisphere of the moon can influence the southern hemisphere because it can toss material that far away. So having crew members have that whole disk view actually enables them to contextualize things they see across the entire disk in a way that we did not get those crew observations in Apollo. But then they also have an 80 to 400 millimeter zoom lens on board for one of their cameras that allows them to zoom into the micro, right? To use that zoom lens to interrogate features of interest that are really compelling for science. The examples that I really am excited about are color and albedo. So actually using the human eyeball, which is an incredibly robust detector, to really describe nuanced color details across the entire disk of the moon. So understanding, this region looks like it has an orange hue, and because of that, we might understand what processes were active in that section of the moon when. So I'm really excited to get that data back.
And there go the first series of parachutes.
After travelling further into space than any human being in history, the Artemis 2 journey ended with a safe splashdown on the 10th of April.
Splashdown confirmed.
Welcome home.
I can't wait to find out what we've learned from this historic mission and these incredible explorers.
But while we wait for more data from robots or astronauts, Pete's here to remind us of the simple joy moon gazing can provide for us here on Earth.
Humans have been looking up at the moon for centuries, its mysterious markings providing inspiration for mythology all around the world, with cultures seeing a man, a rabbit, a frog, and in modern times, even a basketball player. So what are those formations that we can see with the naked eye?
Let's start with the large dark areas. Once thought to be seas, they're called maria, and created by lava flowing into basins to form iron-rich volcanic rock that doesn't reflect much light. Prominent ones to look out for are Oceanus procellarum, the Ocean of Storms, Mare Imbrium, Sea of Showers, with a distinctive semicircular bay known as Sinus Iridum, the Bay of Rainbows, Mare Crisium, the Sea of Crises, Mare Serenitatis, the Sea of Serenity, and Mare Tranquillitatis, the Sea of Tranquility, where Apollo 11 made its historic landing in 1969. The bright areas in between these features are known as the highlands and represent the oldest surface of the Moon. One standout feature in the south is the impressive Tycho crater, whose beautiful rays were created by material that was ejected from the impact that formed it. These spread out virtually across the whole Moon.
The full moon is always impressive to the naked eye, but the direct lighting angle hides its rough and battered surface. To see these relief features, the light has to come in at a shallow angle. I can demonstrate this by shining a torch onto this 3D printed model of the crater Copernicus. If I shine it on directly, you can't see much detail. But if I move the torch around so the light is coming in obliquely, you can see the shadows which define all the surface structure. Incoming sunlight is most oblique near where the illuminated part of the moon meets the part which is dark. That's a line dividing the moon's night and day, and it's known as the lunar terminator.
And it's here with binoculars the details really pop. Great targets to start with are the craters Copernicus, Plato, and Tycho. If you have a small telescope, additional features can be seen, and here my picks would be the amazing Mons Apenninus, the distinctive Valles Alps, and of course the wonderful Clavius crater, which contains many additional craterlets within its walls.
Even if you don't have a telescope, just keep looking up at the moon and watch how its surface and features change from day to day. You never know, you may become hooked and want to progress your lunar journey by moving on to taking photographs of the moon, capturing stunning images like these which have been sent in to our Flickr account.
But we have to end on some of the stunning images taken as Artemis 2 journeyed around the moon, including those of this beautiful and delicate planet that we all call home. Wherever our exploration of the moon takes us, and no matter how long it takes to get people back to the surface, one thing is clear. The renewed global interest in lunar exploration will give us a better understanding of the origins of the moon and allow us to travel further than ever before. So I'll keep on dreaming about landing one day on the lunar surface, and in the meantime, I'll keep looking up at that beautiful orb in the sky, that orb that has shone down on Earth for billions of years. Good night.